Now, perhaps one of the most famous laws of Newton was his third law of motion called the action-reaction law. This law states that for every action, there is an equal and opposite reaction. If we're thinking about numbers, vectors, and forces, if I push an object with 15 newtons in a certain direction, that object will push back at me in the opposite direction with exactly 50 newtons. So there's never any less that comes back to the push or any more that comes back to that push. Whatever I push with is exactly what gets pushed back to me. Now, essentially, doesn't that mean that if I push against the wall, I really don't have much to worry about because it's only going to push back at me with the exact same force? And the same can be said if I run into a wall, right? So I shouldn't get hurt, according to Newton's law of action-reaction. Well, let's test it out and see. So one thing you should have seen or observed is that I moved, but the wall didn't move. Now, if everything is just action and reaction and equal on both sides, how come I moved but the wall didn't move? Does that mean that there's an inaccuracy in Newton's third law? Well, let's take a little look at the numbers and figure that out, at least a little more closely. Now remember, the main formula that describes forces acting on an object is Newton's second law formula, which is mass times acceleration, and this is applicable to all the laws of motion. And so remember that the acceleration really describes something moving. So in physics, when something is moving, it's accelerating. And your net force is your net push or pull. Now, according to the third law, it's the net force that has to be constant. So when we think about the wall and you think about the person running into the wall, the person runs into the wall or exerts a force on the wall of, let's say, 50 newtons, and that wall will exert the exact same force back, 50 newtons. And so while the force is the same, the amount that they move will not be the same. And why is that? Well, when you look at the formula, the third variable is your mass. And we could agree, at least in this case, that the mass of the wall is significantly greater than the mass of the person. I'll just write P. And so if you actually plug in the numbers, you would see that when we isolate, because of the wall's greater mass, the movement of the object pushing the wall would be far greater. More specifically, let's say we assign an arbitrary mass of about 100 kilograms, and we're being, conservative with that estimate. It'd probably be a lot more. And we assign about 60 kilograms to the person. Well, if they're both experiencing a force of 50 newtons, if we think about the wall, and we go 50 newtons is equal to 100 kg multiplied by the acceleration, and we divide both sides by 100 in order to get that acceleration, we would see that the acceleration of the wall would be 0.5 meters per second squared, and that's a lot. It's probably a lot, again, a lot less than this. But you would have some acceleration. Now, if I look at the person here, and we do the same formula, so 50 newtons is equal to, and we go 60 times A is going to give us the net force, and we divide both sides by 60 to isolate for the A. Our acceleration would be about 0.833 repeated meters per second squared. And so we could see that while they both experience the same force of 50 newtons, the acceleration is more for the human being. And again, we were being conservative here. All this really means when you look at the two accelerations is the person moves a lot more. The general rule for this is that the greater the mass of the object, the less acceleration it's going to experience due to a force applied on it. In even more concise terms, the bigger object stays relatively still, while the smaller object moves.